You know, when you're looking at the absolutely incredible, blocky landscapes of Minecraft, or you're lost in the beautiful, sprawling world of Genshin Impact, what you're seeing is, well, it's art. But underneath all of that beauty, your computer sees something totally different. It sees a universe built from nothing but pure numbers, a world governed by the cold, hard logic of matrix mathematics. So how in the world does that happen? I mean, how can a machine that at its very core only understands on or off, 0 or 1, conjure up these massive three-dimensional worlds that feel so real you can get lost in them for hours? That is the big question we're going to unravel together today. We are going to pull back the curtain on what is, no exaggeration, one of the most incredible illusions in all of modern technology. And by the end of this, you'll get the precise mathematical magic that makes it all possible. Okay, so let's map out our journey. To really get it, we're going to follow a single 3D object from the moment it's created as a simple blueprint all the way to that final polished image you see on your screen. First up, we'll look at the blueprint, what a 3D model even is to a computer. Then we'll get into the 2 golden rules. These are the unbreakable laws every single model has to obey to even show up in a game. After that, we'll follow its journey to your screen through this 5-step assembly line called the rendering pipeline. And on that journey, we are going to uncover the great camera deception, a massive illusion that is at the very heart of how 3D games work. And we'll wrap it all up by looking at the unseen miracle, the just staggering amount of math that makes this all happen in the blink of an eye. All right, first things first. Before we can put anything on the screen, we need to understand what a 3D object really is from a computer's perspective. So let's start with the most basic building block, kind of like the digital DNA of everything you see in a game. A computer doesn't see a person or a car or a tree the way we do. It can't really understand concepts like curves or solid surfaces. That's all way too abstract. Instead, what it sees is something called a mesh. And that description on the slide, a digital skeleton, that is the absolute perfect way to think about it. To put it another way, imagine you're an artist, but instead of clay, all you have to build with are straight pins and tiny rubber bands. A mesh is that network of pins and rubber bands that creates the shape of your sculpture. That's all it is. It is just a very, very organized collection of points in 3D space that have been connected to each other. Every single complex, beautifully detailed character you see in a game is, at its heart, just an incredibly sophisticated connect-the-dots puzzle. So how do you actually build one of these digital skeletons? Well, it's a beautifully simple 3-step process. First, an artist places a whole bunch of points in a 3D program. These points are called vertices. Think of them as the dots in our puzzle or the pins in our sculpture analogy. Each one is a very specific X, Y, and Z address in space. Step 2, the computer connects these dots with straight lines. We call these edges. These are the rubber bands that stretch between our pins. And then step 3, and this is the magic part that turns a simple wireframe into something that looks like a surface. It connects 3 vertices together to form a face, and that face is almost always a triangle. Now you might be asking, why a triangle? Why not a square? Well, here's the cool thing. 3 points, no matter where you put them in 3D space, will always create a perfectly flat plane. Think about it. A 4-legged chair can wobble if one leg is a little off, but a 3-legged stool, it never wobbles. It's always stable. Triangles give that same mathematical stability to the 3D world. Every gorgeous curved surface you've ever seen in a game is an illusion, created by stitching together thousands, sometimes millions, of these tiny, flat, stable triangles. Okay, so we have our mesh, but before we can even think about putting it into a game, it has to pass a sort of quality control test. See, it's not enough to just have a bunch of triangles. This mesh has to obey 2 absolutely critical, non-negotiable golden rules of 3D graphics. And if a model breaks either one of these laws, you get all sorts of weird visual bugs, like holes in the world, or sometimes the object just disappears. So the first rule has this kind of mysterious name, winding order. And what it means is that it's not just about which 3 points you connect to make a triangle, it's about the direction you connect them in. Think of it like you're drawing a triangle on a piece of paper. Do you draw the line from point A to B to C? Or do you go from A to C to B? To us, it's the same triangle. But to a computer, that direction is a secret instruction that tells it something vitally important. So what is this secret instruction? Well, this is it. By universal agreement, when an artist connects 3 points in a counterclockwise direction, going against the clock, the computer understands, okay, this is the front of the surface, this is the part I need to draw. But if those same points are connected in a clockwise direction, the computer flags it as a back face, an internal surface that nobody is ever supposed to see. Let me rephrase that. Imagine you have a simple cardboard box. The winding order is like putting a little sticker on each side that says either this is the outside or this is the inside. A counterclockwise order is the outside sticker. A clockwise order is the inside sticker. And this simple little rule is the key to one of the biggest performance-saving tricks in all of computer graphics. And that trick is called back face culling. Just think about it for a second. When you're playing a game, you never see the inside of a solid brick wall, right? Or the inside of a character's head. So why on earth should the computer waste precious energy and time drawing them? The answer is it shouldn't. And thanks to winding order telling it which faces are the back faces, the insides, the computer simply deletes them. It culls them, just throws them away before it even starts the really expensive work of figuring out colors and lighting. This one little trick can literally cut the number of triangles the graphics card has to think about in half. That saves a massive amount of work and lets developers build bigger, more detailed worlds. But it also means if an artist messes up and puts an inside sticker on an outside surface by mistake, that part of the model will just seem to vanish because the computer thinks it's a back face it's supposed to delete. Okay, on to the second golden rule. This one is called topology. Now, if winding order is all about the direction of one single triangle, topology is about the structure of the entire mesh, all the triangles working together. It's the mathematical rule that makes sure a 3D model is a complete, unbroken surface. The keyword here is watertight. Imagine you've got a 3D model of a teacup. If that model has perfect topology, you could pour digital tea into it and it wouldn't leak out. A valid 3D model can't have any random holes or gaps or weird overlapping faces that would let that digital tea spill all over the place. It has to be a perfectly sealed, continuous object. Now, how does a computer actually check for this? It's not like it looks at the model. It uses math, specifically a concept based on Euler's formula. Okay, now don't let this formula scare you. You absolutely do not need to memorize this. The only thing that matters is the idea behind it. Think of it like this. For any sealed-up object, there is a very logical and predictable relationship between its number of corners, the vertices, its number of lines, the edges, and its number of sides, the faces. This formula is just the mathematical way of writing down that relationship. So when the computer gets a new model, it just counts up the V, E, and F, plugs them into the formula, and sees if the equation works. If the numbers don't add up right, the computer knows instantly, hey, this model's topology is broken, it's not watertight. It's a really simple, elegant logic check. So why is this so important? Well, because a model with bad topology, what artists call a non-manifold mesh, it just breaks everything. It completely confuses the physics engine. For example, how is the computer supposed to know how a ball should bounce off a wall if that wall has a tiny invisible hole in it? The ball might just fall right through the world. It also causes chaos for the lighting. You'll see light bleeding through a surface that's supposed to be solid, creating these ugly, strange-looking visual bugs. It's basically like having a blueprint for a house where one wall isn't quite connected to the floor. The whole structure is fundamentally flawed, and that tiny little mistake is going to cause all sorts of problems later on. Okay, so we now have a perfectly valid 3D model. It's a beautiful mesh, it has the right winding order, it has proper topology. So the next big question is, how do we get this thing from a file on a hard drive onto your 2D monitor? Well, welcome to the rendering pipeline. And honestly, the best way to think about this is like a factory assembly line. Our 3D model is the raw material, and it is about to go through a whole series of transformations or spaces to become the final product, a 2D image. This assembly line has 5 main stations, or spaces. And every single vertex of our model, every single point, has to pass through every single one of these spaces to end up on your screen. It starts out in its own little private universe, called object space. Then it gets placed into the shared game universe, called world space. After that, the entire universe gets shifted around so we can see it from the camera's perspective, in view space. Next, that 3D view gets squashed down onto a flat 2D surface in clip space. And finally, that flat image gets mapped to the actual physical pixels on your monitor in screen space. Let's break down this amazing journey one step at a time. The journey always begins in object space, which is sometimes called local space. And here, the model exists in a total vacuum. It's defined by its own little private coordinate system, and its center point is usually right at the origin, the 0, 0, 0 coordinate. Think of this as the original blueprint that the 3D artist made. A car model in object space isn't on a road somewhere. It's just floating in an empty black void, perfectly centered. It has no idea there's a world around it. Another way to think of it is like a toy action figure that's still inside its plastic packaging. It has a shape and a form, but it hasn't been put into the scene yet. All of its points are just defined relative to its own center. Next up, we move into world space. This is where we take our action figure out of its box and place it into the dollhouse. It's where the model finally gets put into the actual game. To do this, the game engine uses these mathematical tools called transformation matrices. Now, I know the word matrix sounds complicated, but for what we're doing, just think of it as a set of instructions. It's just a tidy little grid of numbers that tells the computer exactly how to move, how to rotate, and how to resize every single vertex of our object. So one matrix has the instructions for its position, another one for its rotation, and a third one for its scale. Our car model gets moved from its private little 000 coordinate to a very specific spot on a street, it gets rotated to face the right way, and it gets scaled to the right size. Now here's the clever part. For maximum speed, the computer combines all of those instructions into a single super matrix. It's way, way faster to do one big calculation on every vertex than 3 separate smaller ones. So now we come to the next step, view space. And this is where we find the biggest, most counterintuitive, and honestly most brilliant deception in all of 3D graphics. It's a clever trick that makes this whole rendering process actually possible in real time. So I want you to think about this for a second. When you are running across a huge field in a game, or you're driving a car down a highway, your character and the camera you're looking through are moving through this big, static world, right? When you push the joystick forward, you are moving forward. Are you absolutely sure about that? The truth is the complete opposite. Your camera, your point of view, is permanently locked in place at the center of the universe, at coordinate 000, staring straight ahead. You are not moving at all. You are completely stationary. So to create that powerful illusion that you are the one moving forward, the computer actually grabs the entire world, every single mountain, river, and building, and pulls it backward past your fixed camera. Now, why on earth would it do this? Well, imagine trying to do complicated math homework while you're riding a bumpy moving bus versus doing it at a solid, stable desk. It is so much easier for the computer to do all the final complex math from a fixed, known viewpoint, the desk, than from a camera that's constantly moving around. So instead of moving the camera through the world, the game moves the world to fit the camera's view. It's a truly brilliant, mind-bending shortcut. Okay, so after moving the whole world to fit our camera, we arrive at the next station on the assembly line, clip space. The main goal here is to solve the biggest problem of all. We have a 3D world, but we need to display it on a flat 2D screen. This whole process of flattening our 3D world is called projection. There are 2 main ways to do it. Orthographic projection is the simplest. It just ignores depth completely. An object far away looks the exact same size as an object right up close. This is useful for things like 2D games or maybe architectural plans, but for realism, games use perspective projection. This is what simulates how our eyes actually work. Things that are farther away look smaller. So how does the computer achieve this complex, realistic illusion? Well, it's not some crazy algorithm. It is an unbelievably simple mathematical trick. For every single point, the computer takes its x and y coordinates, its position on the screen, and just divides them by its depth, its z coordinate. That's it. That one simple act of division is what makes distant mountains look small and nearby cars look large. It is the mathematical heart of perspective. Now, before we get our final picture, there's one last absolutely crucial detail we need to make things look real: lighting. To figure out how light should bounce off a surface, the computer has to know which way that surface is facing. Is it pointed towards the light or away from it? It does this using something called a normal vector. The easiest way to picture this is as a tiny little arrow that sticks straight out from the center of every single triangle at a perfect 90-degree angle to the surface. These millions of tiny normals are like signposts that tell the lighting engine how to shade every little piece of the world. But there's a problem. What happens if you take an object and you stretch it out to make it taller or wider? Well, the triangles get stretched, but the normal vectors can get bent and end up pointing in the wrong direction. This would make the lighting look all wrong, with weird dark spots. So, to fix this, the computer has to use yet another special expensive matrix, the inverse transpose matrix, just to fix all the normals and make sure they're always pointing the right way. The point is, even this tiny detail of getting the light right requires its own special layer of complex math. And that brings us to the end of our assembly line. Our objects' points were defined in a mesh, they passed the 2 golden rules, they got placed in the world was moved around our stationary camera, the 3D view was flattened onto a 2D plane, and the lighting directions were all corrected. The very last step, screen space, is actually pretty simple. It just takes that final 2D image and maps it to the grid of pixels on your monitor. What we've just walked through is this unseen miracle of pure math that is happening every single moment you play a video game. Let's just try to put this into perspective for a second. Every single vertex in the entire game world, every corner of every single tree, rock, and character goes through this whole 5-space transformation. This involves millions and millions and millions of matrix calculations. And this isn't happening just once. To get a smooth 60 frames per second, this entire unbelievably complex process has to happen from scratch for every single thing on the screen 60 times, every single second. It's a constant, relentless tidal wave of calculation that your graphics card is specifically designed to handle. So the next time you're exploring some digital world, just take a moment and appreciate what is really going on under the hood. It isn't just a game. It's a symphony of mathematics. It's a constant, high-speed dance of numbers that creates a beautiful and totally convincing illusion. Let's just slowly walk back through the key ideas one last time. It all starts with a mesh. That's the digital skeleton of an object, built from points called vertices connected by edges and formed into flat faces made of triangles. That mesh has to obey 2 golden rules. First, winding order. That's the direction the vertices are connected, which tells the computer which side is the front and which side is the back to be deleted to save power. And second, topology, the math rule that makes sure the model is a complete watertight shape to prevent glitches. Finally, to get that model onto your screen, every point it's made of has to travel through the 5 spaces of the rendering pipeline, from its own private blueprint and object space into the shared game world and world space, seen through the great deception of a stationary camera in view space, flattened from 3D into 2D in clip space, and finally, mapped to your monitor's pixels in screen space. And it's all powered by millions of calculations happening every fraction of a second. So now that you know the hidden math behind all the magic, will you ever see your games the same way again?
If you enjoy this video, please like, share, subscribe and hit the bell to the later update from my channel. Thank you for watching till the end and see you in the next video.